privilège de vous présenter Dr. Walter Herzog. Il a fait ses études de premier cycle en éducation physique à l'École polytechnique fédérale de Zurich en 1979. Par la suite, il a réalisé ses recherches doctorales en biomécanique à l'Université de l'Iowa aux États-Unis en 1985, pour la suite poursuivre des études postdoctorales en neurosciences et biomécanique à Calgary en 1987. Il est présentement professeur de biomécanique en kinésiologie, en médecine, en ingénierie et en médecine vétérinaire. Il est titulaire de la chaire de recherche du Canada en biomécanique cellulaire et moléculaire et de la chaire commémorative Killam en recherche interdisciplinaire de l'Université de Calgary. Ses champs d'intérêt incluent la biomécanique musculo-squelettique, axée sur les mécanismes de contraction des muscles et le rôle de la protéine titine, et la biomécanique des articulations, centrée sur les mécanismes d'apparition et d'évolution de l'arthrose. Walter Herzog est le lauréat du prix Borelli de la Société américaine de biomécanique, du prix Carrière de la Société canadienne de biomécanique, du prix Dyson de la Société internationale de biomécanique du sport, du prix Muybridge de la Société internationale de la biomécanique et, bien entendu, a reçu l'an dernier le prix Killam en génie du Conseil des arts du Canada pour sa contribution à la recherche biomédicale. Il a été président des sociétés internationales américaines et canadiennes de biomécanique et il a été intronisé à la Société royale du Canada en 2013. Donc, sans plus tarder, je vais demander à Dr. Herzog de venir présenter sa conférence sur, intitulée « Rythme moléculaire et du corps humain en mouvement ».
Thank you very much. Thank you very much for the very kind introduction. I'm happy to be here, and I would like to personally thank Andre for making this happen, and of course the University of Montreal and the Killam Foundation and the Canada Council for the Arts. I'm a biomedical engineer, and when I started out as a sport biomechanist. So I studied whole human and animal movement. And then for the past 15 or 20 years, I've slid down more and more into basic research and essentially do only like molecular and cellular biomechanics. So I came from whole human movement down to the molecular and cellular level. And I think that's what I try to explore a little bit with my topic there, rhythm in biomechanics. And I'm going to talk about randomness, rhythm, and synchronicity. And want to convince you that on the very molecular level, things might happen random, and then you ask yourself, how can an organ or a human being or an animal function so perfectly with all the randomness that seems to be going on a lower level? With this in mind, I unfortunately have to give you a basic lecture on muscle, but it's going to be very simple. But what you need to know about muscles is that they are the only thing in the human body that allow you to move. So if I'm moving around, if you dance, if you clap, whatever you're doing, you need muscles. When muscles are not there or they're not connected to the brain, you cannot move. So that's lesson number one. And lesson number two is that on the very lowest level there, you have contractile proteins that make the muscle function. And these contractile proteins are actin and myosin. And you remember that from Biology 30 that you had in high school. So those are the two things that you need to know. And I want to first show you an example of an organ that works very well, and it was mentioned by Dr. Hashinsky already this morning, and that is the human heart. So here you see the electrical activity of a human heart and the sound, and it's not perfectly periodic. Because a human heart doesn't go periodic, but the signal, the electrical signal that it shows, that shows its coordination, is absolutely perfect and is essentially the same all the time. A second example that I want to show you about from sport, and not only rhythm and periodicity, but also a great amount of synchrony, is shown here with these rowers from the New Zealand national team on a training run. And as you appreciate, these rowers have to be in absolute synchrony. They have to be very periodic. And that is helped by this little man on the left-hand side that is there on the screen. That's called the coxswain. And the coxswain actually gives the rhythm, so yells out whatever they yell, but they keep the people in rhythm. And they could row by themselves, but with the coxswain, they're just that little bit more precise. It's kind of like what we saw this morning, a conductor in front of an orchestra. You don't really need the conductor. The orchestra could still play, but the precision and the accuracy would not be there. It would not be the kind of same piece of music, and it's the same in sport. So we see that obviously the human heart works perfectly, people can interact and synchronize, and we all believe that. But now I want to start out on the level of muscle contraction and talk first about muscle contraction before I go into the other 4 topics. And I want to convince you that there is a randomness that's happening there, and then you have to ask yourself, from that randomness, how can we be so good and have controlled movements? And this goes really back to the basic understanding of the cross-bridge theory. This was formulated by Andrew Huxley in 1957, Nobel Prize winner, and you have the interaction of the myosin filament with the actin filament. And so here, what you have is that this M site, the myosin, needs to interact with the A site there on the actin, and that happens in a stochastic way, because the way Huxley described it and the way we believe about this happening is that there is Brownian motion that leads the myosin head to the actin. And Brownian motion, of course, is purely random. So I cannot ever tell you exactly when the myosin is going to attach to the actin. I can write down an equation and say, oh, over the next 10 milliseconds, there is such a possibility or a probability that it will attach, but I can never exactly tell you when it attaches. And this is kind of illustrated here a little bit in this random movement of the cross-bridge head before it attaches to the actin filament there. So the middle part there is regular formation of the molecular way on how such a cross-bridge looks like. And this is an interaction powered initially by Brownian motion, and so is therefore random. And now I also want to introduce a second randomness, and that is how a muscle fiber in a muscle is activated. And you know that you need to have a connection to the brain through a nerve, a motor axon, and that motor axon fires at a certain frequency when you do a certain movement. And so let's say, for example, the motor axon fires at 50 hertz. That means it would come on every 20 milliseconds. But it does not come on every 20 milliseconds. It comes on after 7 milliseconds, after 13, after 19, after 33, after 25. It's a random process how they fire. And on average, it will fire, let's say, 50 times. But in actuality, you never really know when a motor axon is exactly going to fire. You can only calculate probabilities in how that's going. And so here we have this randomness on the motor unit activation side. We have the randomness on muscle contraction. And so then the question becomes, how can this all be coordinated? The next video that I'm going to be showing you here is an electrical measurement of a muscle. And you hear when the motor units are activated. So you see it with the electrical signal that's shown, but you will also hear it, because each of these bumps that you hear, if these are firing, these are cracking, is a motor unit activation. And listen if you think this is synchrony or harmonious. Maybe you heard a synchrony, maybe you heard a certain activation pattern. For me, this is pure noise. It's unpredictable. You never really know when one thing happens after the other. And so the question then became for me, well, how might this all be synchronized? Because we know that in animal and human movement, we can achieve absolutely incredible things. And I want to show you a couple of videos that I personally think are some of the most amazing animal or human movements. The first one is this cheetah running after prey, and not only is a single muscle perfectly contracting at the right time, the whole animal is coordinated. All muscles play in synchrony for this animal to be able to run at 120 kilometers per hour. And then to go to a human example, well, we have a field of sport called rhythmic gymnastics. And it's about music, it's about interacting with the environment. It is rhythmic. And I think, I took this video and I think it's so perfect that, at least for me, it was almost impossible that this woman who is showing this performance here with the ball routine can do that. So I think you would agree with me, this is rhythm, this is perfection in movement. If I hadn't seen this, I wouldn't even believe that what she was doing there is even possible. And so I think we agree all that there is obviously certain human movements that are very rhythmical and everything. But in the following, I want to talk about rhythm in a sense where it might not be so obvious. And I chose the example of javelin throwing. And I'm just going to throw you a javelin throw here by the world's best javelin thrower, the world record holder. This is Jan Zelezny throwing the javelin here. And you just watch what he's doing. And, maybe you saw some rhythm there, maybe you did not. But you don't essentially think about javelin throwing as a rhythmic event. The reason why I chose javelin throwing is because I used to throw the javelin when I was young, and I coached javelin throwers. I taught little kids how to throw the javelin. I mentored and coached national champions, and I coached an athlete who went to the Olympic Games in javelin throwing. So I don't know much about rhythm, but I was thinking about the only time in my life that I ever thought about rhythm was not in science, but it was in coaching and teaching. Because what a javelin thrower does is as follows. I'm going to show you another one, and you watch the last 5 steps of this particular javelin thrower. This is the number 2 thrower in the world. This is Thomas Röhler from Germany. And this is actually the second best throw ever to be done. And here he is, and watch the last few steps there. And if you saw that, there is a very distinct rhythm. And when I taught javelin throwing, I taught it with rhythm and with counting out the steps and with doing the movements, because what a javelin thrower tries to do, is in the last 3 steps, he or she tries to bring the lower body forward in front of the javelin such that the acceleration path is the biggest, but then, since they run relatively fast, they have to stop almost abruptly. So they run relatively fast, and then they stop abruptly. And the way you do that is as follows. And excuse me, I'm a left-handed thrower, so I'm different than those two, but I'm a left-handed thrower. The way you do that is you have the 5th to last step, 4th to last step, and now you make a jump, and you throw the upper body forward, and then you try to land really, really quickly. And the rhythm is 1, 2, yantadam, 1, 2, yantadam, 1, 2, yantadam. That's the rhythm of javelin throwing. And other throwing events in track and field are the same, and hurdling is the same. You have this certain rhythm in events that you probably wouldn't think about. And we were taught as coaches and as physical education educators to use rhythm in our classes for the learning and for the teaching. So that was one of the examples that I wanted to show where it's not so obvious. I don't think people look at javelin throwing and say, oh, this is rhythm. I always said, this is like dancing. Discus throwing is like dancing. High jumping, the last few steps, is like dancing. You have to get that rhythm down in order to have a good performance. If you don't do that, the performance is not there. We know that animals and humans have pattern generators on the spinal cord level and on the brain level. And we also know that sometimes these pattern generators are perturbed And I'm going into an area now that's not really directly me, that probably refers much more to Dr. Hashinsky. But in dementia or in Parkinson's, people will have movement disorders. And one of the movement disorders is that they get this freezing movement behavior or the freezing gait. And I'm just going to show you this little video where this is demonstrated, and then what rhythm or music does in some of these patients, not in all of them, but what he might be doing. So have a little bit.
Balance is affected as well. So what John has, you can see here, is a freezing of gait, and the feet are sticking to the floor.
But watch what happens when we start the music. It's beautiful to watch.
It is, it's so beautiful. And for a person...
And so for some reason, when the rhythm comes in and you watch, it's not only the music, the woman actually clicks with her fingers, and there's videos out there where you just have a metronome, and just a metronome is enough. You provide a certain rhythm, and then through that rhythm, something happens that is not quite explainable to me, that seems to get rid of certain inhibitions that you have in those pattern generators that produce locomotion. And so music is, and the rhythm is a healing pattern in certain diseases with the brain that we have. And so with this now, I want to go a step further and not only talk about rhythm, but with the rowing boat, I showed you that there's a certain synchronization in there. And earlier this morning, we heard and saw that some animals, are able to kind of mimic each other movements but it's in a fairly rude way, in a fairly crude way, and 100 animals could not really do that together. The only animal that seems to be able to spontaneously, in big group, organize themselves in a certain way when you give a command, seem to be humans. And so I'm going to make this little example here with you, a little test that I got from Stephen Strogatz here when he has this TED Talk on synchronization. And the exercise is, and now everybody has to be very active. Now you have to listen. If you didn't listen at all, you have to listen now because you have to do something. You have to clap. And I want you to clap in synchrony. And if Steve Strogatz is correct, then people can actually do that. So I'm going to say 1, 2, 3, clap. And then I would like all of you to clap. But not only clap, I would like you to clap in synchrony. So everybody's ready? We haven't trained this. We haven't prepared for this. Here we go. This is the for real now. 1, 2, 3, clap. You go on. You want in synchrony? Exactly. That's it. Bravo. Bravo. People can do that. No other animal can do that in a big group, that you give them a command and do that. And although when you clapped early this morning or at my introduction or so, everybody clapped and you were out of sync. Some people clapped a little earlier, some a little later. We can tell you, and there are certain patterns that emerge when people clap. There's just a pattern that's a little bit stronger than another, and people are very, very good at zooming in on that and then immediately adopt that. And within 2 or 3 seconds, you can get into synchrony. And I don't need to show you this next video because that's what it's all about. So we can, through hearing and audio clues, like in rowing and in clapping, we can get synchronized. I want to show another entrainment on synchronization. And we talked a lot about bridges. Dr. Hashinsky and Dr. Goudreau were talking about bridges. I'm going to be talking about bridges as well. And here we go. Here we talk about bridges.
The bridge opened on the 10th of June, 2000, attracting thousands of people and the media. But as the people poured over the bridge, it was clear something was wrong. The bridge was wobbling from side to side.
The bridge was wobbling from side to side, and the engineers were called on the opening day, and they didn't really know what's happening. They knew that the bridge would be vibrating a little bit, but didn't realize that the bridge would be wobbling so much that it actually became dangerous, and they had to control how many people they let on there. And Natalia, of course, I invited, is an engineer, and she would know exactly the solution why this all happened. And it was mentioned a little bit this morning with soldiers marching in step. I was in the Swiss Army when I was 20 years old. You come to a bridge, you're not allowed to walk in step because you might excite the bridge at its natural frequency. And so here we go.
Something unexpected happened. People changed the way they walked in reaction to the movement of the bridge. To balance themselves, pedestrians spread their feet apart, creating a significant lateral, not vertical force. More importantly, the people's reaction was almost identical. Everyone stepped the same way at the same time, creating a synchronized rather than random force. The frequency of this force matched the natural frequency of the bridge.
The motion of the crowd was synchronized with
synchronized movement, not through sound or not through anything that anybody said, but through the vibration of a system. And then the small vibrations were taken up, and as soon as the small vibrations were there, people starting to get synchronized, and they started walking like that because they didn't want to lose balance. And in a very simple way, we can mimic that with a very simple experiment. Now I'm going to show you systems, a couple of systems that are going to become synchronized purely because of the physics of it, and it's all the mechanics. And so here, the initial one that I'm going to show you is these two pendulum that are on this, suspended on this bridge. They are arbitrarily out of synchrony let go, and then you see that the bridge starts wobbling, and when the bridge starts wobbling, it accelerates one of the pendula and decelerates the other one, and they are clearly not happy. They are an unstable mathematical system. You can prove mathematically that they are not happy there, and when you then wait a little bit, a minute or so, then they get into perfect synchrony, mechanically speaking, purely because of the physics, where the pendula go to the left, the bridge goes to the right, and the bridge goes to the left, and the pendulum goes to the right, and so it does that. And you can do this example with many other things. So these are metronomes, again, activated purely arbitrarily and randomly, and then they are on this frictionless, bridge, I call it now. If they were on a tabletop that is essentially not moving, and therefore not exerting forces on them, they would never ever get synchronized. They would stay exactly out of synchrony as they were organized. But because of the mechanics of the system, this is a kind of Newton's law. There's no external force acting on it because it's in the whole system, and therefore the center of mass has to stay in the middle. So if the pendulum goes to the left, the bridge will go to the right, and so that the center of mass stays always the same. And then again, you wait long enough, and when you wait long enough, then they are perfectly in synchrony, and the mass of the pendula goes to the left, the table goes to the right, vice versa. So this is an entrainment that it doesn't require any brain, no feedback. It's purely based on the physics and the laws of physics, and so I thought that was an interesting thing. And then I'm gonna finish up my talk here with showing a last example. And again, that was mentioned earlier this morning. Somebody asked about the behavior of many animals, flocks of birds or fish or insects or also caribou, and how they behave in a certain way. And although we don't really know exactly why they do it, we can mathematically model it. And I would argue now that this is a system that, at least for me, doesn't really have a rhythm, but it definitely has harmony and synchrony, and it produces very nice pictures. So these are thousands of starlings that were filmed, and they form these intricate patterns, and they fly in this particular way in big groups in order to avoid predators. It has been shown that it's much harder for a predator to capture a single bird when they are in a group like that compared to when they're flying alone. So this is an evolutionary thing, it seems, where the people, the starlings, where they have learned how to survive by flying in this particular way. And then you ask yourself, well, why do they exactly fly that way? And I'm not sure, as I said, if we know why they fly that way, but we can mathematically, with 3 very simple rules, we can mimic that. And here is an explanation. So now we see here these starlings flying, but this is a mathematical animation. This is not a.
Every starling in the flock is following 3 simple rules. Firstly, as you fly, steer towards each other. Secondly, if any of your 7 neighbours turn, then you turn. Finally, don't crowd each other. Amazingly, that's all there is to it.
There's just 3 basic rules. First of all, they want to stay together, but they don't want to crowd themselves too much, so they have this safety sphere around them. And of course, they need that because when their neighbor makes a little turn, they need to have time to react without flying into one another. And then the last thing is that they do what the neighbor is doing. And then there's a couple of other rules there. Another rule is that they like to stay around a certain area, for example, a feeding place or a nesting place. And so they don't migrate like that, but their center of mass always stays about at the same place. And of course, when a predator comes, then they go apart, and as soon as the predator is through, they come together again. So I thought this was beautiful how with some very simple mathematics, we can explain a synchrony and an entrainment here in how animal behavior might be working. So, summarizing my little talk here, what did I want to try to explain? Well, the first thing that I tried to convince you of, that on the molecular level and the level that I normally work, things happen randomly, and we describe it with stochastic equations. We cannot have deterministic equations, but nevertheless, and that is particularly true for muscle that I try to illustrate, but nevertheless, the muscle, of course, works perfectly. I can exactly and smoothly move my arm, despite the fact that on the molecular level, this is all random. And similarly, the second thing that I wanted to say is that rhythm is inherent in our movement systems. We know that we have hardwired pattern generators in animal systems. In some animal systems, they're very explicit, so much so that you can essentially separate the animal from the brain, and through the pattern generators, the animals are still able to perform locomotor movement because they are hardwired pattern generators that are rhythmic on the spinal cord level. And more amazingly, at least for me, and that's what I learned, is that with the rhythm and with music, you can overcome certain inhibitions that you might have with certain diseases. And then finally, what I wanted to demonstrate is that synchronization is possible on all kinds of levels. For the clapping that you did, you seem to need human beings. I'm not sure exactly what it is about human beings that is required, but then you can also cause synchronization through an external agent, through sound. You know, if I clap like this and I ask you to clap with me, you can very, very easily do it. Or through the mechanics of a system, as I try to illustrate with the bridge there, it just follows the laws of physics, and you, as a particle of the system, just fall into that. And it can also occur purely spontaneously. And with spontaneously, I meant the bird example. There's no higher force, there's no sound, there is no rhythm, there's no mechanics that dictates how these birds fly in synchrony without bumping into each other, but some very local rules that govern each single bird seem to be able to explain that very, very nicely. So with this, I would like to thank Andre and Vladimir again, primarily for them, having had the idea and, really go through all the pragmatism of getting this organized. Thank you very much.
That was amazing, but there's so many things, and I'm trying to think of everything that you've shown, and I had to write down a few notes. You started with at the muscular level, at the molecular level, right? And you said you have muscle contraction, and which is random. You said that statistically you can say in such a time we will have this that will occur, but it's not. It's random. And then you continued with movement control at a higher level. And then you skipped to the third point with the animal-human movement, and we see that cheetah running, and the other one was the rhythmic gymnastics. And it's so perfect, so suddenly so perfect. But you've been talking that everything was random, and then to me it's as if there's something missing in between. And I don't get that, how you can get to that perfect movement. What do you know what can happen in between?
Yeah. The one thing that I didn't mention about the randomness is, and again, this is really boring old mathematics, but what I said was perfectly correct, that when you have one myosin molecule interacting with an actin, that's essentially a Brownian motion, a random event. But when you have many of these myosins, many of these motors connected to one another on a backbone like the myosin filament, if you then write down the equations with the noise term in there, and you have thousands or millions of these motors, the random noise actually cancels out. And when mathematically the noise then cancels out, and therefore, mathematically speaking, you then get a very deterministic system. So although a single actin-myosin interaction is random, as soon as you have thousands or millions of them, then it's not random anymore, because the noise term falls away. So it's a relatively simple solution.
But you mainly work at the molecular level, right?
Yeah, I work mostly on the molecular level, and I'm interested in these stochastic mechanisms of actin-myosin interaction and protein unfolding and protein interacting with one another and not interact, well, and releasing from each other, yes.
Because I have to say, it's been, 15, 20 years that I attend your conferences?
Yeah.
First as graduate student at the Canadian Society of Biomechanics, and then at other levels, international conferences, and always seen you talking about these at the nanometers or micrometers.
I like to talk about little things, yes.
And you're still, and when you look at this, and how, just to talk about your research, how are you able to extract these? Because to me it seems interesting. If you look at rhythm, you said it's stochastic, and I think in engineering or sciences, lots is stochastic. So for us, it's a little difficult to understand all that rhythm. For me, first, rhythm is linked to music, to art, and when it comes to our level of research, it's quite far away. But can you have something to say about that?
I'm not really sure how you go then from that. The only thing that I do know is that when you go from that very, very tiny level, where the laws of physics are different than Newton's laws, because viscosity becomes a big thing, Brownian motion becomes a big thing, and lots of things on a molecular level are controlled controlled or randomly assembled and function that way, that on a higher level, magically it comes together in a functioning system. And that's what I try to show with the functioning heart. Because, the interesting thing is, of course, then once a fiber in a muscle or in a heart is activated, then, of course, synchrony comes in, because then all the force-producing elements, all the sarcomeres in that fiber will essentially be activated at the same time. And so from this random process, on a certain level, on about the cellular level or the multicellular level, that's when things become organized and synchronized. And I think that is what allows our organs, our muscles, our heart to function in the way they do.
Well, first of all, thank you for conveying very complex concepts with compelling clarity.
Thank you.
I want to ask you whether this idea that randomness is important has an explanation in complex systems. My understanding is if you arrange nodes in a circle, and connect them, the distance between any given two is far. If you change one at random, all of a sudden they all become closer together. And this explains why the internet, for example, has just a few major nodes, and it's called a small world network. So I just wonder whether just as in complex system, the randomness enhances connectivity, whether having a little bit of noise, as you said this morning, or the idea that randomness begins ultimately in order is important to make systems more connected.
You know, I can't really answer that question, as you know, whether or not the randomness really helps in the connectivity. And the example that he gave is a very interesting one that works in this particular framework. But what I do know is that on a molecular level, things are governed primarily by stochastic means, by random means, and somehow at one level the organization needs to come in, and it appears therefore that in everyday life, if we go small enough, then randomness will become very, very important, becomes the governing force and the governing way how systems interact. But that's not true anymore as soon as you go a level higher, where all of a sudden, magically, things start becoming organized and synchronized. And that's why we can function.
If I may, a complementary question.
Sure.
Most people believe that Einstein got his Nobel Prize because of relativity. He didn't. It had to do with explaining Brownian motion. So clearly he must have had some mathematics to explain it. So what was it that he discovered or described that deserved such an award?
Well, Albert Einstein wrote that very famous paper. That's the only paper I ever cite from Albert Einstein because I don't understand the other ones. But I cite his 1905 paper, where exactly he describes Brownian motion mathematically and in a probabilistic way. And so he introduced essentially stochastic mechanics there, and then was able to explain many phenomena. And of course, then that was also taken as the building block for quantum mechanics, this randomness that is persistent in quantum mechanics as well. And so, yes, he's very famous for that paper, and that's the one paper that I cite all the time, because it's the classic paper in the area where he describes what happens in Brownian motion. But just to be absolutely clear, it's a probabilistic description. Not even Einstein could describe where a particle goes next, where you could say the probability of this particle being here in 20 milliseconds from now is 2% or 5% or 17%. He could do that, but he couldn't say, and nobody can, not even Albert Einstein, predict exactly where a particle is going.
Well, didn't Heisenberg later discover his principle that you can know where an electron is, but not what its charge is? Isn't that right?
Yeah, it's kind of, you can either know where it is, but not its velocity, or you can know its velocity, but not where it is. Yeah.
Right.
Yeah.
Thank you.
Thanks.
Well, thank you so much for your presentation. What I particularly appreciated that you started from the micro level and then you moved up to the flock and the swarm behavior at the end, showing very organized synchronization explained by very simple rules of proximity at the end. Now, if we come back at the human level, so it seems like, and this is something that we see more and more at the behavioral level, that synchronizing to a predictable stimulus, can be a metronome, it can be the music pulse, leads to a benefit. You show the example of Parkinson. This is a nice example of the way in which basically Parkinson can benefit from an external pulse in their motor behavior. And my question is, so is there any evidence showing that by synchronizing to an external timekeeper, we have benefits which trickle down to the muscle synergy level, so the lowest micro level that you showed at the very beginning? Yeah.
That is a very interesting question, and unfortunately, I am not aware of any evidence that actually shows that. What music and rhythm seems to do, though, is it seems like on a neuromuscular control level, it seems to be helpful. But whether or not it actually does something on the muscular level and how the muscle contracts, I'm not aware of any of that at all.
Yeah, because I mean, we have evidence that at the level of, higher control mechanisms, cortical and subcortical structure, of course, as you said, there are top-down mechanisms which act on the central pattern generator, so they have to some extent, but we don't know exactly. So my question really was, we know what's going on at the level of the muscles, but as you say,
I don't think, I think I would be aware of that, I'm pretty sure, if rhythm or rhythmic movements or movements that are performed, with a certain metronome or so, whether or not they cause a different behavior in the muscle. That would actually be something that could be tested relatively easy because we can measure the electromyographical activity of a muscle.
This is what we're doing in my lab. I wanted to be sure that we don't have any evidence on that.
Yeah, and that is actually something that could be tested. That's a fairly wild idea.
Good.
But yeah.
Thank you so much.
Yeah.
Thank you for a wonderful talk.
Thanks, Janet.
As I was listening, as you were moving from the random level to the organized level, to the synchronized level, I was expecting to hear you say the word refractory period for some of the higher order biological systems, that the random movement might activate. So even, is it the actin? In the randomness in the muscle fiber.
The actin-myosin, yeah.
Yeah, the actin-myosin, that, I mean, I don't know anything about it. I can barely repeat the term.
Yep.
But does that have a refractory period in being able to sort of like synthesize or generate the next? So that's what, and then you got to resonance. That's what the other, so I was just wondering whether sort of refractory periods at biological systems at different levels are part of what turns randomness into synchronicity. And
that could very well be. And I'm thanking you for a question that I can actually answer, because yes, there is a certain refractory period of actin-myosin interactions, because each actin-myosin interaction is coupled with the hydrolysis of an ATP, an adenosine triphosphate, and therefore the chemical processes take a certain amount of time, and therefore you cannot have a cross-bridge attached 700 times per second. And similarly, of course, we know nerve has a refractory period as well, when the action potential is traveling down. For reversing it and becoming like a resting potential again, that takes a couple of milliseconds. So when you stimulate a nerve at 50 hertz, you get a lot of force. When you stimulate it at 1,000 hertz, you get no force, because you continuously go into the refractory period, and the nerve is never really ready to actually transmit that signal. Yeah. So refractory periods, as an interesting thought actually, refractory periods indeed might cause a certain rhythm that you cannot exceed, at least as an upper limit.
Yeah, and then there might be like parallel fibers or interneurons or something that,
Yeah, and of course, and when you have these interneurons and the feedback pathways, and so they all take a millisecond, to kind of synapse and go. So there are refractory periods, because muscles are very, very slow in reacting. If I'm activating a muscle and I'm saying, okay, I'm going now and activating a muscle, within milliseconds I can see the electrical signal, but before I have maximum force, that takes about, in a normal human muscle, takes about 250 or 300 milliseconds. So we are fairly slow in building up force.
Yeah, I guess that was my question. Great, thanks.
And I should have thought about refractory periods, but I didn't. You're absolutely right.
Oui, je vais parler lentement pour que Walter comprenne bien ce que je dis.
Oh, yeah.
C'est intéressant. Bon, j'ai été très intéressé par la présentation parce que tu nous as présenté et fasciné par certaines images et aussi par certains résultats. Pour moi, c'est incroyable de voir que la musique permettait donc à des personnes avec des problèmes au cerveau, mettons, de retrouver le rythme, etc., etc. Bon, d'une part. Par ailleurs, toujours dans l'optique de créer des ponts, quand c'est bien qu'on soit ensemble parce que j'entends des choses qui résonnent chez moi. Je ne sais pas comment faire le pont, puis on le fera peut-être jamais ou on le fera un jour, mais la fameuse stochastique, c'est quelque chose de fondamental. C'est pas très connu en cinéma, malheureusement, mais de plus en plus, j'imagine, fondamental que nous avons perdu avec l'accession du cinéma au numérique. C'est-à-dire que c'est ce qu'on appelle la stochastique des selles d'argent. La pellicule cinématographique, la plupart des jeunes ici n'ont jamais vu une pellicule cinématographique, elle fonctionne sur un rapport aléatoire de la distribution des selles d'argent. Ce qui fait qu'à la limite, il n'y a pas une copie de film qui ressemble à l'autre. Chaque frame, mettons, a une distribution différente de l'autre frame avant, de l'autre frame après. Il n'y a pas un photogramme semblable sur le plan de la distribution de la stochastique ou des selles d'argent. Donc, c'est totalement aléatoire. Et donc, ça a un effet sur le rendu sur l'écran qu'on ne peut plus retrouver avec le numérique. Peut-être avec le numérique qui copie un film déjà en argentique, mais un film tourné en numérique, lui, il n'y a plus rien d'aléatoire, tout est synchronisé, c'est des chiffres, un haut, c'est de l'informatique, quoi. Donc, il y a quelque chose, il y a une pulsion de l'image qui est disparue. Qui fait que quand on fait un freeze frame, un arrêt sur image, on sent toujours un mouvement dans l'image, même si, parce que chacun des photogrammes qui passent arrêtés a une distribution différente des selles d'argent. Voilà. Donc, éventuellement, on pourra penser à voir comment ces questions-là peuvent se poser pareillement ou différemment d'un secteur à l'autre. Voilà. Ce n'est pas une question.
Okay.
Merci, parce que j'aurais eu de la difficulté à la traduire. Il comprend bien.
Well, I understood pretty much what you said, but I'm happy that I don't need to answer it because it would go beyond my knowledge. Yeah, but it's an interesting analogy, the stochasticity in the film and how the film then comes together and how that forms a nice synchronized image that we can comprehend. It's a great analogy. Yeah.
A brief clarification question. You said, well, things begin at random, but then they have order. Was your explanation that random movements cancel each other, so you end up with a pure product?
My explanation on molecular level exactly was not really that they cancel each other, but I'm relying purely on mathematics here. The noise, when you write down an equation how a molecule interacts with another one, then you have a certain equation plus a noise term. And you do that for a second one and a third one, and you do that for thousands. And if that noise is random, then in a system of many, many random noises, the noise cancels each other out, and then the whole system becomes deterministic. That's what I tried to say.
Yeah, I'll try to simplify it even further.
Okay.
For example, you said one interval could be 10 seconds,
Yep.
then 13 seconds, 9 seconds. If you have enough of those, mathematically you average them out and they come down to 0, right? Is that the same idea?
Yep, it's exactly the same idea. You can think of it two dimensions as a Gaussian distribution, and you know one particle goes here, one goes there, one goes there, one goes there, and then when you average a whole bunch of them and you calculate the mean, exactly, then it becomes 0, or it becomes the mean, whatever the mean is.
Yep. Thank you.
Yeah, that's exactly it.
Merci beaucoup.
Thank you very much. Thank you.